Hello again, and welcome back to Spotlight Live from Climate Solutions News. I'm Dominic Shales, and I'm a publisher of CSN. Today, we're turning our attention to the Arctic, and in particular, the sea ice that's vanishing faster than ever before recorded. According to recent data from NASA and the Copernicus Climate Change Service, Arctic sea ice just hit the lowest winter maximum in nearly 50 years of satellite monitoring, which is really shocking. And this matters because sea ice isn't just frozen water. It acts as Earth's reflective surface and shield, helping to cool the planet. And as it disappears, global temperatures rise even faster. And to help us understand what can be done, we're joined by Dr. Joshua Elliott, Chief Scientist at Renaissance Philanthropy. Joshua is a leading expert in climate resilience with a background in systems modeling, food security, and climate risk. He's advised global institutions on climate adaptation and is actively engaged in evaluating innovative approaches to slow or reverse Arctic ice loss. But I hope I've done you justice, Joshua, and please do feel free to add anything else.
That sounds great. Thanks.
Very good. So welcome and thanks very much for joining us, and let's dive straight in. So to kick things off, can you tell us a little bit about Renaissance Philanthropy?
Sure. So we actually launched just about a year ago with the goal of generally trying to accelerate the amount of philanthropic giving that goes into science and technology. And we do that in a very specific way by, not just by advising philanthropies, but by actually creating programs and philanthropic funds that have sort of have a time-bound thesis, are led by an expert field strategist, and are really trying to actually accelerate to some sort of an impact, and not just sort of continuously, funding, basic research, et cetera. We like to sit at the area of what we call translational R&D, which is taking the basic research and the insights that are coming out of science and actually translating them to the point where they can scale and have actual real world impact in the world, and in the kind of in the finite time we have to do so.
Very good. And give us an example or a couple of examples of the kind of work that you're involved in directly.
So the most relevant one here is an initiative that we're just about to launch publicly, that we've been incubating for a while, called Advanced Research for Climate Emergencies, which is really looking at catastrophic climate risks in the future that are either severely underfunded or completely ignored, and then developing expert-led, mission-driven programs to be able to explore and better understand potential opportunities for either mitigating those risks upstream, whether that's the West Antarctic ice sheet or the Arctic, or coral large-scale coral death, or in trying to build resilience in the human system to those catastrophic risks. The first program that we worked on, for example, is called the Arret Glacier Initiative, which just launched a couple of weeks ago, which is looking at developing the modeling, monitoring, and engineering technologies to see if we can stabilize the West Antarctic ice sheet to avoid catastrophic sea level rise scenarios.
Very good. And we'll put a link in the underneath the in the notes so people can go and look at that. So just coming back to the research that Copernicus Climate Change Service and NASA did, I think Copernicus reported that the ice extent was 6% below average this year, which is the lowest maximum cover in 47 years, according to the satellite data record. And similarly, NASA and the National Snow and Ice Data Center observed in March that the Arctic sea ice reached its annual maximum extent of 14.33 million square kilometers, the lowest ever recorded. So how immediate is the need for intervention to prevent further depletion? Because it sounds pretty grim.
It certainly is grim. And I mean, I think that sadly, the fact is that this data came as a surprise to effectively no one, right? So these trends have been ongoing for a very long time, and they will continue. I think, for me, the thing that really hits me the most is the fact that if you measure the sea ice by volume, we have lost approximately 3/4 of the volume of Arctic sea ice in the last 40 years. 75% of the volume of Arctic sea ice. I mean, that's just absolutely shocking. And there's a lot of reasons to be concerned about this. I mean, first of all, the best estimates right now are that the Arctic is likely to be completely free of ice in the summertime at its minimum by 2035. That's 10 years from now, which is, on our timescales of sort of, climate innovation and policy, might as well be tomorrow. So we are really working against the clock, and the other part of it that kind of troubles me on this is that Arctic sea ice decline has consistently accelerated further than any of our models and science has predicted that it would, meaning that there's still a lot of things that we don't understand about the Arctic and about particularly about our Arctic feedback loops, particularly the loss of albedo that you mentioned, with much darker oceans absorbing a lot more sunlight and temperature.
And in terms of what we can do about it, are we just too late, or are there actually technologies or approaches that you think could go to both halting the decline and even reversing it?
Yeah, it's a good question. We're definitely not too late in the absolute sense, but we probably should have gotten started a lot sooner. So the one approach that actually has gotten some attention and some effort in it is an approach called sea ice thickening, which involves typically drilling holes through the Arctic sea ice and actually pumping water onto the ice during the winter months in order to allow it to freeze and thicken and then become ideally more robust to melting during the summer. So there's been a few different efforts on that front, and we've seen some good results, but honestly, results have been mixed, and there's significant challenges, unfortunately, with trying to scale that approach over extremely wide areas. You need energy for pumping, you need all sorts of different things, but people continue to make advances in that, trying to find ways of improving that. For example, reducing the amount of salt that's in the water. One problem with the sea ice thickening is the thing that you're actually freezing on top of the ice is salt water rather than fresh water. And the Arctic sea ice is actually fresh water because the salt actually dilutes out of it as it freezes. And unfortunately, as we know, salt water melts at a lower temperature than salty ice melts at a lower temperature than fresh ice. And so, but there have been some efforts at trying to improve that, saying how can we actually get some of the salt out of it. So there's some promise. There's also some companies that are looking at, can we create unmanned drones that can actually drill up through the ice from below and pump water in, that might make things more scalable. But it's a massive scalability challenge.
But just for reference, I mean, obviously 75% of the ice is gone, as you said at the start. How thick is the ice now? It's obviously thinner than it was, but what's the general thickness?
I don't know that off the top of my head. I mean, obviously it varies wildly down to the edge, but I don't know, what the peak thickness is in the middle. I'm not sure. That's a good question for the drilling. I mean, most of the drilling and pumping would be happening largely at the sort of edge of the stable sea ice in order to thicken that portion of it. So I'm assuming it would be happening in the relatively thin portion, but I don't know.
And you mentioned that there were some trials or kind of pilot programs doing that. Are they continuing, or are they needing more funding, or what's the stage of those projects?
Yeah. So there's at least two companies and multiple different academic groups that have been exploring this. So the Cambridge Center for Climate Repair has been looking at this at Arctic sea ice thickening for a while. There's a company called Arctic Reflections that's been working on this, and another one called, I believe it's Real Ice, is another, probably the most farthest along on this process. Both of those have been approaching this from trying to find a scalable business model within the ice thickening realm, which is a challenge, as you might imagine. Some people have proposed things like an ice credits market, similar to carbon credits, to fund this kind of work. But I think most people think that's unlikely, particularly in the current environment. But who knows? Certainly, like the countries, particularly the Scandinavian countries, have a very strong interest in seeing this happen, as well as other countries around the globe. I mean, so there's been a lot of great work recently by this group called IGSD, their Indian counterpart, on the connection between sea ice loss and disruptions to the Indian monsoon. So, there's a saying in the Arctic that what happens in the Arctic doesn't stay in the Arctic. We're now seeing the ramifications of that as Arctic sea ice declines, and we see sort of impacts and teleconnections to weather patterns around the globe.
Very interesting.
So, one of the things that we're looking at is we're trying to identify approaches that we hope can be much more scalable, cost effective, and feasible in the Arctic. So the first one that we're really excited about is one that has the scientific name of mixed phase cloud thinning, but would be commonly referred to as cloud seeding in the Arctic winter, effectively. The same thing that we do above ski resorts to make snow for people to ski on. We can do that in the to supercooled to clouds that have supercooled water in the Arctic during the wintertime, and we can thin those clouds, which means making them more transparent to outgoing infrared radiation, which allows the Arctic to cool and get colder, particularly in the winter months, and should allow more ice to reform. The early modeling studies on mixed phase cloud thinning indicate that you can probably cool the Arctic by about 1 degree Celsius on average just from this single intervention. Now, that's not going to solve all the problems, but it will help slow down sea ice decline. It will help reduce the risk of tundra destabilization and resulting methane emissions. It will help reduce the rate of Greenland melt and ice loss. Ultimately, though, the solutions in the Arctic are going to have to require a sort of a portfolio of different options, and that's why the work we're doing is trying to look very broadly across how do we not just find the silver bullet, because honestly, hopefully we know by now in climate that there are no silver bullets, that everything requires a portfolio and a kind of an all-in approach.
And with the cloud thinning, is that is much more scalable, is it, than in terms of economic cost?
It should be much more scalable in terms of economic cost. Yeah. We've done some just, back of the envelope techno-economic assessments, and, we sort of estimate that in principle, particularly with modern improvements to drone-based cloud seeding, you might be able to implement it globally for throughout the entire Arctic for a cost as low as several $100 million a year. Would be an incredible ROI in terms of the amount of damage averted. ROI of many orders of magnitude.
Which is crazy, isn't it? The total cost implication of not doing it. I've also heard about other cloud technologies that could be brought in, which is sort of using clouds as reflective surfaces to try and beat off more of the sun's rays in the first place. Do those have any merit?
Yeah, so marine cloud brightening is the most popular way for that, where you effectively spray some aerosol, usually aerosolized seawater, up into the lower cloud layer. And those aerosols actually help to nucleate cloud particles and make clouds more reflective, brighter. Sometimes making more clouds where there might not be clouds, but there's the right humidity conditions for clouds, and sometimes just making the existing clouds brighter. There's a number of challenges, as I understand it, with implementing marine cloud brightening in the Arctic. It's not totally clear how well it will work, largely because of the cold conditions, and because, in fact, of the mixed phase clouds I was just referring to, where mixed phase just means that you have both ice and water in the cloud at the same time.
It can't be that good to be pumping chemicals up into the air to try
Well,
and.
I mean, in this case, it's just salt water, right? So it's not chemicals, which is nice. That's one of the very good parts about MCB. But that's another thing that we're looking at. For example, it may be mixed phase cloud thinning only works in the wintertime when it's dark, because you don't want to thin the clouds in the summer, because then they won't block as much light. So there may be options, for example, where you can do marine cloud brightening for a few months a year in the summer to reflect more sun, mixed phase cloud thinning in the winter. Marine cloud brightening still has some pretty severe implementation and scalability challenges. It almost certainly has to be done from ships, particularly if you want to cover a significantly large area. Of course, operating in the Arctic at all has huge challenges, and trying to scale anything across wide areas when you're doing it from the ground. That's basically the nice thing. Anything you can do from the sky rather than from the ground is going to be much easier to scale.
I also read about another potential solution that doesn't sound very practical, but reflective geotextile blankets that have been used on some glaciers, apparently, to some effect. But just the scale surely can't be big enough to have any impact.
The scale, and then of course you can't help but worry about the sort of secondary environmental outcomes of it. So I'm not sure if you're familiar with this this project that was spreading. I'm not familiar enough to know the details, so apologies, but they were spreading small, highly reflective particles across the ice. I believe primarily experimenting in Greenland. And they recently had to close the project down, I believe primarily because it was identified that the materials they're using might have some sort of negative environmental consequences in terms of building up around the environment. So anytime you're introducing a synthetic or alternative material within the environment, you really have to be careful about what the secondary environmental consequences might be of that. But I am familiar with with the reflective textiles. And again, certainly interesting, but as you say, the scale is pretty daunting.
So are there any other promising technologies that haven't come on stream yet that you think could have benefit?
Well, I mean, you certainly have to consider Arctic-focused stratospheric aerosol injection as another highly scalable method. So, as you probably know, stratospheric aerosol injection is the most, sort of the most I'd say well studied and popular method for global sunlight management. It's the thing when people think of geoengineering, that's what they think of. Let's imitate volcanoes and spray particles into the stratosphere where they can last for a long time and reflect some small fraction, usually 0.5 to 1.5, 2% of the incoming solar radiation. It's certainly possible. In fact, it's easier to do that in the Arctic than it is even at the tropical latitudes, because the stratosphere is actually lower in the Arctic. We have plenty of airplanes right now that can easily access the Arctic stratosphere, whereas in the tropical latitudes that's not true. So that one's certainly worth considering. It's certainly worth having on the table and evaluating. There are, of course, a lot of, let's say, social license and geopolitical concerns, and some very valid environmental concerns with stratospheric aerosol injection that have to be carefully considered. But it's something that very much deserves more research in order to try and understand what those factors are. And then there's actually just a very long list potentially of ideas that have been proposed for the Arctic in general, not necessarily specifically for sea ice, but there's ideas for using porous wooden platforms as ice seeds that can help ice to be able to grow faster in the winter time, so that it declines less in the summer. There's quite a few options out there. Taking old abandoned oil platforms that are no longer being used for drilling and parking them in the Arctic so that they can again be used for as sort of seeds to help the ice be able to grow and stabilize for a longer time. So there's a variety of ideas out there, ranging from the very interesting to the potentially not terribly credible. But there's no doubt that we need as much creativity as possible. One interesting thing that's actually being done is in the category. It's not a huge effect, but is reducing contrails, or rather optimizing contrails from airplanes. So Breakthrough Energy spun out an organization recently, last year or the year before, that works with airlines in order to optimize their flight paths, or tweak their flight paths and other factors, I think, of operation, in order to primarily to reduce their contrails. However, I think they're also looking at places where it might actually be climate benefit to increase contrails in certain situations. And in the Arctic, is perhaps the prime example for this. And we, of course, do have a lot of commercial flights in the Arctic that pass through the Arctic. So I think it's a little too early to say, or I don't have the numbers at least on what the total effect could be. But just even optimizing the sort of flights that we already have going through there could have some effect. And it is something that's being actively worked on.
Yeah, I think that was a project that Google was also involved in, wasn't it? To optimize the flight patterns and things. I remember hearing about that. So key question, Joshua. Are you hopeful that we can come and deliver the solutions on time?
I am hopeful. Yes. Let's say I am hopeful. I don't think that I would be doing the work that I am if I wasn't hopeful. We're have this as a very high priority for us. We're going to start incubating a program that we've been working on for a while, quite soon. That's called the Arctic Climate Emergency Response Program, to try and drive more investment into this space of doing kind of responsible R&D in order to build solutions and to build the necessary sort of scientific basis for the kind of hard decisions that that governments and the intergovernmental community are going to have to make in the very near future about these kinds of questions. So for those reasons, I'm clearly hopeful because I'm trying to dedicate significant energy to working on this. I do think though that we have waited too long, and I do think that no matter what we do, we are likely going to be experiencing, in fact, we already are experiencing, significant increases in severe weather patterns and other effects from how badly we've sort of let the Arctic get out of balance effectively. So it's not a problem that we're going to solve immediately, and it's not a problem that we're going to solve without suffering some sort of consequences. But I certainly do hope that it's something that we can at least address at some point before we just get completely beyond the point where anything can be done.
Having started by hearing of the 75% ice loss, you've made me a little bit more hopeful. So thank you for
Good.
that. And
Good.
it's been great to hear all about some of the solutions that could come online. Obviously, some more difficult than others, some more practical than others. But let's keep our fingers crossed that some of these are the major breakthroughs that we need. So, Dr. Joshua Elliott from Renaissance Philanthropy, thank you very much for talking to us.
Yeah, thank you. It was great.